My name is Dave Ullman. I titled this Electric Airplanes Hype, and I on purpose did not put punctuation after the word hype. And I'll let you decide whether there should be an exclamation, a question mark, or a period. That's for you to decide. In the description, I posed 4 statements, and I'm going to tell you the end so you can leave here now if you want to and go do something more useful. But I said electric propulsion will change what airplanes look like and how they'll fly. I think the answer to that is a resounding yes. Okay?
Good?
What?
Do you need me to tap out to get sound off your computer or anything?
No, I'm good. Will the current eVTOL concepts change aviation? Yes, but not soon. And I'll explain why I say the but not soon. Will you be able to pull out your IC engine and replace it with an electric motor anytime soon? Well, you can sort of do that, but you don't go very far. We can talk about that too. And what's the promise of distributed electric propulsion? What I should have really written there was propulsion airframe interaction, because that's really where my hot spot is, as you'll see as we go through this. I'm going to make a lot of predictions. Does anybody here speak Danish? You do? Oh, good. Did I translate this correctly? Damn. Well, I've been led to believe it says it's difficult to make predictions, especially about the future. And I'm going to make a lot of predictions. So you're not going to agree with me. And anything I say isn't right. And everything's out of date anyway, because I updated these slides yesterday, but they're out of date today. So that's the way it goes. My background, I've got degrees in aerospace. I got a PhD in mechanical. I worked at the Flight Dynamics lab way back when Orville and Wilbur were still there. I write textbooks on stuff. And I started playing around with electric aviation in 2009. And I've been working with CubCrafters, and we'll get into that project a little bit, since 2019. I've written a number of articles. I was a keynote speaker in 2018 at the Cafe Symposium, and some of this material is actually from that 2018 because basic science has not changed in the past 5 years. With my partner, Vince. Vince, are you here? Vince Homer? Oh, he's abandoned me already. Vince and I got our first patent back about 4 years ago, and then we got another patent with CubCrafters about 1.5 years ago. In 2019, I started flying this airplane. This was my Jabaroo, which I cleverly had recommissioned as an experimental amateur built, and that's a different story. And I put ducted fans on it. They're 120 millimeter diameter ducted fans. And the whole theory there was if you can accelerate the air over the wing, you can gain a lot of lift. And it turns out I lowered, with just 4 of these things on there, 3 kilowatts each, I knocked three knots off the stall speed. And there's a lot of potential here. So this was my early foray into that. More recently, I've been working with CubCrafters. This is an airplane I'll describe to you in just a few minutes. It's called ELAS. We were flight testing this just 6 weeks ago. Our test pilot, Len Fox, is in the audience here today to make sure I don't tell too many falsehoods about that. But what I want to do is I want to do a big picture and then zero in on my little corner of it. So, because I know there's people in the audience that know nothing about electric aviation, and there's other people in here that know a lot about something. So I'm going to try to hit on everybody. But this is a big deal. There's a lot of money floating around out there in investments. And I've just found a couple of them off the web, and these are all fairly recent. And we're talking billions of dollars people are investing. So this is serious stuff. So about 10 years ago, I was rebuilding an IO 360 with the help of an old A&P mechanic. And I told him I was starting to look into electric propulsion, and his only question was how long is the extension cord? And we've come past that. So there's a lot of players here. This is an out-of-date slide. It would have been out of date even if I'd updated it in the last couple of weeks. But there are a lot of players, and over 200, I'm sure. And, you know, these aren't all going to survive. Some of them are going to percolate to the top, and others will disappear. So in the title of this talk, I put hype. And the reason I put hype is this is one of my favorite diagrams. It's by Gartner. Gartner is a research organization, and the Gartner hype cycle is fairly well known, and it pertains to just about any technology you want, any new technology. And it says initially there's going to be a peak of inflated expectations. We can do everything. We can save the world. And then, of course, reality sets in as you really try to build it and make it work, and you end up in the trough of disillusionment. And then you slowly get enlightened and you come out someplace with a plateau of productivity. And this may be fairly low, it may be fairly high, you just don't know. And I think overall, we're at someplace near the top of the disillusionment. And the stuff that I'm working on, which is propulsion airframe interaction, is actually much further down that slope because people have just barely started looking at it. And I'll make that clear. So this is where the title comes from, and this is what I think's happening. So you can, I don't think things are mature enough that there's clear classes of air vehicles. This is my first cut at that, where we have the traditional aircraft, called eSTOL. The quadcopters, the dual power, you got one power to get up, another power to go forward. You have rotating thrust. And then the propulsive airframe interaction, which I'm going to get to, and there's a YouTube link there. By the way, if you go to www.davidullman.com and then go to my Aero tab, you'll find most of this information. People are looking at all kinds of different missions. UAM is the big push, which is now called Advanced Air Mobility, and that both terms seem to be used. STOL enhancement, which is an area that I'm working on a lot now. Humanitarian, getting in and out of tight places to bring in and out people and goods. People are looking at sport, we'll show that, and of course the military has lots of missions. On the UAM, Uber published this list, and it goes over 2 slides, of what UAM means to them. This was published about 6 years ago, and at first I looked at this and I said, you know, this is a really dumb mission. And then the more I thought about it, I thought Uber did a really good thing, because they stuck a stake in the ground and they said, here's something we can try to achieve. Be it realistic, be it unrealistic, who knows, but here's something we can try to achieve. And what they visualized was you could get your Uber car, you could get the Uber driver to take you to this little heliport kind of thing, and there would be an Uber airplane waiting for you, or an Uber some kind of vehicle that would lift you up, take you across the city, plink you down. There'd be another Uber car waiting for you to take you to your final destination. Really a good vision. And here's some of the things they said that it needed to do. One of them I want to point out in particular is the 4th one. They said that they thought at the time it would take batteries at 300 kilowatt hours per kilogram, 300 watt hours per kilogram to make this happen. Now batteries, you got to talk about how much energy is in a battery per unit weight. And I'll get to that again in just a second, but 300 is still ambitious and we're still not there. Some more of the same list. They visualized doing 3 or 4 passengers. They visualized a range of 100 kilometers with some reserve and cruise at 150 miles an hour or 130 knots. So this was just one set of a mission description that they had, but it's one that people have latched onto and modified over time. So I found this on the web just the other day. Here was one company's visualization of the UAM mission. All those little dots are different vehicles. There's a couple things, it's a sort of dumb diagram because actually the little vehicles they have in there are actually rotated 90 degrees from the way they're supposed to be, but we're not being picky here. But the thing to take away from this slide is that there's a lot of them. And to make this pencil out, to make this vision that Uber had pencil out, you have to have a lot of throughput if you're going to make any dent at all in ground transportation, and when that was their goal. So there's a lot of them in this picture, and that's as it should be. The other thing it brings up is, how are you going to manage this airspace? And a lot of people are looking into, you know, this is their whole research, is how are you going to manage this type of airspace? You know, obviously these have to be autonomous vehicles because there's no way each one of these could be piloted by a different person and not cause total chaos. And as you go around and talk to different people that are doing electric vehicles, you'll find some are keen on autonomous and some are keen on piloted. And I'll address that slightly as we go also. So here's my one slide on batteries. When I talk about batteries here, there's lots of alternatives. There's fuel cells. There's all kinds of ways to get electricity. Batteries are the biggie. And I'll talk between helicopters. The column you want to look at is the furthest most column to the right, and that's deliverable. Often you'll hear people quote some kind of an energy density or a power density for a battery, and it's for a cell. And the cell's only a small part of the whole package to get the energy to anything useful. So you can easily get reliable batteries in the 200 watt-hours per kilogram range. That's what we've been using. An awful lot of the other companies that have been working on getting vehicles going have been thinking they'll have much denser, much higher energy densities. That's fine if you're going, but it ain't going to be here today. You might notice that avgas is much more than an order of magnitude more dense in energy. You might also notice that the theory for lithium is an order of magnitude higher than where we are now. Keep in mind, battery research for running cars stopped in about 1905. Okay, as soon as the electric starter was developed by Bendix, electric cars went away. And so we've had IC engines being developed for 130 years, 140 years. Battery development stopped for vehicles and then didn't start up again until the last 20, 30 years. So it's still early days in developing really good batteries. So let's just look at a couple different airplanes, and I'll give my opinions on them. And again, you know, this is all my opinion. Take it or leave it. A couple years ago, they took out an IC engine and put the electric engine in the Beaver. I know it flew. I don't know if they use it at all. I don't know what's happened to the airplane, but this is a good case. Alice is a really interesting one. It's quite a lovely airplane, and I actually looked at their website 2 different times in history. Once was about a year ago, where this main slide comes from, and you might notice you can see 440 under the front of it, and that's the nautical miles they predicted. And then the gray strip at the bottom is I pulled off just the other day. All the other specs are pretty much the same, but they're now saying 250 nautical miles. I think some of that little going over the hype cycle and coming down into the reality part said, oh, with the batteries that are available, we can't really get 440 nautical miles, but we might be able to get 250. We'll have to see what they say at a later time, but I thought that was interesting that the website had moved. And they're not the only, I've seen this with other websites too, so I'm not picking on Alice at all. Airbus is sponsoring the electric racers. This is a really good mission for electrics because they only have to stay up for 20 minutes, 15, 20 minutes. So you can just suck a battery dry to do the mission, and you're done. You can come down, recharge, swap the batteries out. I don't know how this is coming along. I haven't seen them announce anything. Pipestrel, which doesn't have their own booth here this year, but seems to be in a number of different booths. They've been marketing the Alpha Electro. It has about a 50-minute range, and they're selling it for a trainer, and that's about right, because typically you take somebody up for an hour in a training. So they found a nice mission niche for taking out an IC engine and putting electric and saving money. So one of the big pushes that got the distributed electric going is the NASA X-57 Maxwell. And to some degree, it does some propulsion airframe interaction. And what I mean by that is that the thrust from the motors are not only pushing it forward, but they're interacting with the airfoil in a way to change the aerodynamics. And they don't do it in as dramatic a way as I think it needs to be done, but they were doing it. And this project was canceled 2 months ago, and there's a vestige of it over in the NASA tent that you can talk to people about it. So they still have it, they're still showing it there. Tecnam, who manufactured the fuselage that they were using, actually had a program where they were doing what they called their P-Volt, and they shelved that also 2 months ago because the energy densities they said the batteries aren't there yet. We're going to shelve this for a while and come back and revisit it. The other class, another class that's worth talking about are the quadcopters. There's just two examples of the more popular ones. The Airbus project, which ended a couple of years ago, had the rotating wings with the rotors on it, and there's a zillion different configurations of how do you put propellers and wings so different things rotate. So you can go from vertical to horizontal. And somebody's going to come along in the next few years and draw a nice little graph that shows all the relationships of these different things that you can rotate and not rotate and try to transition from vertical to horizontal. I haven't seen that yet. Joby's doing a tilting rotor, and they're after the UAM space. Here's the vehicle in another configuration. Just last month, they were cleared for production by the FAA. They've gotten a lot of money from Delta and Toyota. So they're right now the big boys in this space. If you look at Joby stock, this is 3 days ago. It's showing in the stock. So if you were interested in investing in this space, maybe that's one you should do. There's a lot of them that are dual power. This is the Whisk airplane they flew yesterday. This is actually 1 generation old. Whisk has a tent down here with Boeing, and they have another configuration where they've gotten rid of the motor to propel them forward after the fuselage on this. Horizon has another one where they have lots of ducted fans to lift, and their propulsion forward is another propeller in the back. People are doing all kinds of really interesting things. How it's all going to shake out, who knows? One of my favorites, and I need to preface this, I'm a technologist. I'm a nerd. I really like elegant solutions. I like pushing the envelope of technology. So putting rotors on something to make it go up doesn't really thrill me too much. But doing something clever with some ducted fans, that gets my attention. And I think Lilium has done that. Now, you got to be careful with Lilium because they get some good press and some bad press. The bad press they get has to do with financial. They've raised a lot of money, and they've made a lot of claims that some investors think are not realistic, and hence their stock has gone way, way down. This is a 5-year running average, a 5-year history. And it's down to 164. That was $1.64. That was as of 3 or 4 days ago. But they've got G1 certification. They're the European Aviation safety agency has blessed them, and they're trying to set up these airports so they can go from city to city doing the UAM. What I'm most fascinated about is I've been watching their projections for range and velocity and how much weight they can do, because about 6 years ago I developed a little model based on some standard aerodynamic methodologies where if you tell me how many people you want to carry and you tell me what range you want, I can sort of calculate how much batteries you can have and how much airframe you can have, and sort of take that apart. And I can do a sniff test really well on the claims. And sometimes I agree with what they're claiming and sometimes I don't. So I'm going to get to that, back to that in just a second. But what I think is really interesting about Lilium is they do make use of the propulsion airframe interaction, PAI. They're pushing ducted fans. You'll see on the various projects I'm involved in, I use model airplane ducted fans because there are a lot of them out there and you can find the most efficient and use them. They claim their battery cell packs have energy densities of 320 to 330, and I haven't seen those batteries yet. That's all I'll say about that. You know, they claim in different places, they've claimed different ranges. They're shooting for a 7-seater. But what I really find fascinating is how they've made use of the ducted fans. They're on the trailing edge. The trailing edge can tilt down like you see here. And what happens is as they use the ducted fan in this configuration, they're not only getting a vertical thrust for vertical, but they're also drawing air over the top surface of the wing. And drawing air over the top surface of the wing creates a low pressure which helps lift. And so they are using the thrust, if you will, or in this case, the intake, if you will, to gain lift to help with the vertical, to get off the ground vertically. And I find that elegant and really interesting. Based on my simulation tool, I ran a whole bunch of simulations here. The only ones to bother to look at are the ones that are in red. And the thing to look at is look at the number of people on board and look at the range going out. And so what I was trying to do was get the range to 250 nautical miles, because that's what they claimed at the time I did this simulation. And you can see over there it does all 250. But then when you come back and you look at the number of people and you look at the size of the vehicle they might need with different density batteries, so I've got 300 and 400 out here, to get to the 7 people and that range, you need energy densities of 400 watt hours per kilogram, and we're nowhere near that. So they've had to back down to some of these others that are more realistic. But it's going to come. You know, batteries, like I said, batteries were not researched for this kind of application for most of the 20th century. So it's going to happen. Another elegant solution that's here is the BlackFly. And it's been here for 4 years, 5 years. And what I find interesting about the BlackFly is they rotate everything. There's nothing moves. The airplane rocks back so you can get it to go up, and then rocks forward so you can get it to go forward. It's a one place. It doesn't have much range. It's going to be sold as a little sport, sort of a toy in a way, and it's never going to be a real contributor to UAM or any of the other major uses that we might have. So this is my really quick survey of the different kinds of vehicles. There's over 200. I could have gone on for hours and hours about differences between these, but I wanted to give you a sort of an overview because it helps with the rest of this talk. So let's talk about propulsion airframe interaction. And I've already mentioned it a couple times, and it's where the propulsors actively alter the aerodynamics. So keep in mind, you can have little ducted fans or other kinds of thrusters You can put them all over the airplane. You can put the air where you want it. If you understand the aerodynamics well enough, you might be able to totally change how an airplane behaves. And I think this is really under-researched, dramatically under-researched. I think the funding agencies have looked at the quadcopters and other things that are really simple technically, but are very limited. And I think this is something that's just it's going to evolve. Lilium does it fairly well. X57 does it some. It allows electric STOL in ways that I'll show you in just a few minutes. And it's actually got some history, so this is not new with us. So the history starts with a guy named Willard Custer. And a book just came out earlier this year called The Speed of Air. It was written by Willard Custer's grandson and a researcher from Georgia Tech. And Willard's great quotation is, "It's the speed of the air, not the airspeed." And what Willard came up with, and he was not an engineer and clearly not a businessman, what Willard came up with is if you take an airfoil and you blow air across it, the faster you can get the air going, the lower the pressure and the more lift you can get. And he came up with this because he got caught in a tornado and he ran into a barn and the barn roof lifted off. And he said, "How did that happen?" And that was his great epiphany. He spent the rest of his life trying to make this technology into something that he could turn into a business. Here's a picture of him with the CCW2. CCW stands for Custer Channel Wing. And there's Willard sitting in it. And this is what I just described to you. He put his motors on, he was working with IC engines with propellers, and he put them on the trailing edge of the wing and sucked the air over the top surface in order to create more lift. When I first stumbled across the Custer Channel Wing, I didn't find this photograph until quite a while later. And it turned out one of the demonstrations that he would do is he'd take one of his airplanes, and he built 5 or 6 different models, and he'd tie it to a pole, and he'd fire it up and watch it lift vertically, because there was enough air flowing over the top surface of the wing to create enough lift to raise the airplane all by itself. Now you might notice there's nobody in the cockpit. Okay, so he's cheating a little bit. You might also look really closely at a lot of the videos that are online with these different companies that are making vehicles right now, and a lot of them don't have people in the cockpit. And if a sizable percentage of your mass that you're lifting are the payload, and you don't have the payload in there, it does get a little bit easier. But the thing to really look at here is the wheels are off the ground. And I found that a fairly amazing photograph. Willard went on to build many different models. This is the CCW5. Willard was he never really understood the technology. He was a very poor businessman. By the time he was done, he was sued by the SEC. The patent office wasn't giving him the patents he wanted, and the FAA was not allowing him to fly. Other than that, he did really, really well. And this is over a 40-year period. He was battling these 3 agencies. You got to give him credit for sticking with it. That's for sure. So this is in the 40s, 50s, moves into the 60s. Then the Air Force gets interested and funds the YC-14 by Boeing. And so Boeing built 2 of these airplanes. The engines are in really close, so if you have an engine out, you don't end up with really bad yaw. Do keep in mind that if you're getting lift out of this, if you get an engine out, you not only have a thrust asymmetry, you now have a lift asymmetry too. And that could be really interesting. You can see in this slide, they're taking the jet exhaust and ducting it over the latter half of the airfoil. Here it is with the flaps down. They did some real trickery about sucking on the flaps. they were able to turn, in some of their experiments, they were able to turn the flow about 70, 80 degrees. And that's pretty substantial. So not only are they getting the low pressure, but then the exhaust is also squirting down. This project was canceled. Like all these projects, if they take 5 or 8 years to do, by the time they get ready to say we can produce these, the funding has moved on to something else. NASA picked up on this a little bit later with their QSRA. By the way, if you want to buy this particular airplane, it's sitting out on a field, and you might be able to get it. I tried to buy it. I don't know what I would have done with it. But anyway, it's got 4 engines and pushes the technology even further. What we're trying to do is Custer tried to create low pressure and lift in the channel where the propeller was. The YC-14 had a single propulsor inboard. The QSRA had 2 propulsors next to each other. And we're saying, well, if you can play with the whole wing. And you can mold how you want the lift distributed on that wing if you do it right. And I don't know that we're doing it right, but we're playing and we're making progress. So this is some wind tunnel results from a couple of years ago. And this was for a 4414, I think, airfoil. And the bottom curve is a lift curve slope for just the airfoil in the tunnel by itself. And if you're not familiar, this is how much lift you're getting non-dimensionalized versus the angle of attack. And typically this goes up until it stalls. The stall's the peak on the blue line. And then if we blow air over the top surface of the same wing, we can shift that curve up dramatically. We can shift the stall point outboard. Actually, this stops at 20 degrees because our equipment wouldn't let us get beyond 20 degrees. So I don't really know exactly where it stalls. But I do know that the 1415 of the unsupplemented, if you will, or the unaugmented airfoil, we've added at least 5 degrees, and we've almost doubled the lift coefficient. So something to think about. There's a big push on this vertical, and the vertical, to get vertical takeoff and landing, eats up a lot of power. It's a dramatic amount of power. But if you do a STOL kind of vehicle, where you've got a really short runway, you can use much less power. And this is a figure that gives you some idea of what happens there. So if we take a STOL vehicle, and this was just for 2 passengers and reasonable batteries, we get down under 100 feet for about half the power of the vertical. If you want to go for 250 feet, you can get 1/7 the power of vertical. So it says, well, do you really need to get vertical takeoff and landing? Or if you can get in and out of a soccer field or a football field, is that sufficient? So I think there's, you know, the helicopters have never taken over everything. Maybe you don't need vertical. Maybe just short is sufficient. And that's the approach that we've been taking. If you go back to the presentation I did about 5 years ago for the Sustainable Aviation Conference, I developed a model where I could look at all kinds of different vehicles. And this is just a representative plot that's available. And what it basically says is what's the range you can get versus the total energy stored in a battery as you're carrying 2 passengers and with near future batteries. And near future batteries were 300 watt-hours per kilogram. And whether you understand this plot or not makes very little difference, but what's important is that no matter how big you make the machine for this particular situation, you're never going to get more than 50 miles out of a quadcopter. You're going to get bigger and bigger and bigger and bigger, but every time you get bigger, you're going to add more batteries, it's going to limit you, and it's almost like it asymptotically approaches. Now this isn't true with internal combustion. These types of plots are unique for electric. And as you can see, if you do an eVTOL, where you use a lot of energy to get up and then you use much less energy to go to your next, to go where you're going, still it asymptotically approaches something in the 150 mile range for this particular situation. Whereas if you don't have to do anything vertical, you can just take off in a short distance, you again almost double the range. So it's just to give you a feel. I've got a couple other plots here. I don't want to go into them, but I've generated plots for all the different number of passengers and batteries that are available now versus batteries in the near future versus batteries in the far future. And all the plots look the same. The message is real clear. If you want to go really far, you don't want to do a quadcopter, okay? If you want to go further than a eVTOL, then you ought to be looking at doing short takeoff and landing because you can get almost double the range, regardless of the size, regardless of the batteries, regardless of all these things. So I think all the emphasis on eVTOL, I think it's correct, but I think it's swallowed up the oxygen that should be going into some other areas. Just my opinion. So now I want to switch hats. I'm taking off my EAA 292 hat and I'm putting on my CubCrafters hat. So I'm now talking as CubCrafters. So one of the other things that came out of the Uber conference was I met Pat Horgan. And Pat Horgan is the CEO of CubCrafters. And Pat and I started noodling around with Vince Homer. Vince, did you ever show up? There he is. Do your hat again, Vince. So any question I can't answer, Vince will make up something. Because he and I we do a lot of work together. Anyway, so at the Uber conference, Vince and I met Pat. And we started noodling around on what can you do with ducted fans and what can you do with leading edge slats and can you do a synergy between the two? And out of this came a second patent that's assigned to CubCrafters that has the ducted fans embedded in slats. This photograph right here is about 6 weeks ago during our flight testing. Len Fox was our test pilot. Len, stick your hand up. Len's a really good test pilot. The amount of data that he took was just amazing. I'll be reducing data for the next 2 months at least. Lots of data. Now, you might notice on here, there's 6 ducted fans on each wing. They're in modules of 2. You might also notice there's 2 sets inboard, then a space and 1 outboard. We did this set of experiments so we could move these around because we didn't understand and still don't really understand what part of the wings we want to affect and how we want to affect them. So this is still very, very much a work in progress. This is funded by NASA. We're in a phase 2. We're about a little over halfway through a phase 2 STTR with NASA. And then we also have Oklahoma State University working with us. Ryan, are you here? Ryan over here is Oklahoma State University helping us out on that. A timeline on all this, just to give you some idea how all this evolved, is Vince Homer and I were doing work in the even before 2016 on the ducted fans by themselves. CubCrafters was doing the slat research. We meet at the Uber Elevate conference. Soon thereafter, we have what's called the ideal patent. That's the patent for the standalone, and that's just Mr. Homer and myself. That's before we really started working with CubCrafters. Then we spin off this ELAS project. Also in 2019, Mr. Homer and I had a booth here. They had a tent for bleeding edge kinds of technologies, and we manned that tent for the whole 7 days and talked to a lot of people, maybe some of you. And then we pick up the NASA funding and get the patent on the combination of slats and ducted fans, and then the flight testing was just in the last month. So this is sort of the timeline how all this came about. So the goal here is to leverage the propulsion airframe interaction to get eSTOL, and I mentioned football pitches. There's football pitches everywhere. They're for soccer, they're 330 feet long. If you can get in and out reliably at 330 feet without a big headwind, you can get a lot. You can do a lot of things that you can't do at prepared airports, and so that's what we're after. The other thing we're doing that is a little bit unique here is that everything on this test airplane was off the shelf. COTS means commercial off the shelf. So the ducted fans, the controllers, the computers, the batteries, everything was off the shelf. Now, a lot of custom packaging and a lot of custom code for the software, but you know, a lot of the other people are everything is custom that they're working on, which is making development much more difficult. So, to give you some idea, these are the ducted fans we happen to be using. They're 90 millimeter, commonly available. The controllers are out of a company that's in Bend, Oregon, that they helped us reprogram the firmware in, but that's all we changed. The battery modules are out of a Model Y Tesla, which are fairly safe. They've been around for a while. The computers we're using are controller computers. So it helps a lot to use proven stuff and not be reinventing all the wheels all at the same time. I really love this picture. Len's flying the airplane with, what is that, Mount Baker in the background? And this is part of our testing. The post up on top has a camera that's doing 360 degrees. This airplane is fully tufted, has little pieces of yarn all over it, thousands of them. And we can see what the flow's doing all the time. Like I mentioned, this was just a month ago, so fairly recent stuff. So where are we? Well, we're, yeah, I shouldn't have put phase 1, phase 2 there. That's a little confusing. The phase 1 is our phase 1 of testing, not phase 1 of NASA funding. But the test went quite well. We got a lot of data. We learned a lot. We'll do some more testing later this fall. The beauty of working with CubCrafters is if this looks like it, it wants to head towards a product. And there's a market for it. It's an established company. We know how to get there. A lot of the other companies don't have this advantage. So here's just another picture of us taking in a takeoff situation. Just pretend there's a football field there someplace. So we aren't giving any results yet because we're still evaluating. You know, we think this whole thing about using the propulsion to change the aerodynamics really has a lot of potential. I'm sure it's under-researched. I know it's under-researched. We'll see what kind of system evolves out of this. And that's pretty much where we're heading. So I want to recap. And these are the questions that I posed at the very beginning. It's the same slide. And will electric propulsion change what airplanes look like and how they fly? Yep. Do we know what that looks like now? Nope. You know, people are trying all kinds of really interesting things, makes it really exciting as far as I'm concerned. Will the current eVTOL concepts change aviation? Yes, but I don't personally think it's going to be that soon because of the battery limitations. By the way, just a little rule of thumb, batteries are increasing in energy density at about 7% a year. Okay, but and lots of people have lots of promises and there's lots of alternatives from batteries. Something will happen, but it's happening slowly. Will you be able to pull out the IC engine and replace the electric motor anytime soon? You can, but you can't get much range out of it at this point. So is it something you want to do? Probably not yet. Is there a promise of distributed electric propulsion? It's really high, especially propulsion airframe interaction. I think it's really high. It just needs to be researched more. I think we're entering a second golden age of aviation. I think airplanes are going to change. When we come back in 10 years, there's going to be a lot of different things we're going to be looking at. Is that going to get down to the guy building or the lady building something in their garage? It may well. It may well. I don't know. So that's my prepared talk. And I figured with an audience this big, there'd be an awful lot of interesting questions. So I'm willing to take a crack at them. So stick your hand up. I'll repeat the question and answer it as best I can. Sir?
What is the difference in takeoff distance to one modified IC plane and ESTOL?
So his question was, how much are we shortening the takeoff distance by adding these ducted fans? I'm not going to tell you. We're still reducing data. We can shorten things a lot. Ma'am.
Does the weight of the battery, like for the Tesla Model Y, that's a vehicle, does that impact the weight of the aircraft?
Her question was, does the weight of the batteries affect the performance of the aircraft? One of the beauties of the approach that we're taking is we only need energy for taking off and landing. We're not cruising on it. So our batteries can be very small because they don't have to store much energy. So once you get to saying, okay, I'm not only going to take off and land on this, but I'm going to do my mission on it, now you're talking that the weight of the batteries can be a substantial driving percentage of the weight of the vehicle. Yeah, good question. Sir?
You haven't mentioned any wind tunnel testing. I would imagine that with wind tunnel testing and modeling, you can figure out placement of your ducted.
His question was, I haven't mentioned wind tunnel testing. How many of you came to my talk yesterday on wind tunnels? Yeah, okay. So there's a whole bunch. So a lot of wind tunnel testing. And because, I mean, some of the things, if you start thinking about this, let's say you want to put a ducted fan in front of a wing so that it's blowing the air over the wing. Do you put it really far in front? Do you put it close? Do you put it high? Do you put it low? Do you tilt it? What do you do? Who knows? There's no theory on this. You can do computational fluid dynamic models, but you can also do wind tunnel models, and we've done a lot of both. So yeah, a lot of that. Sir, be really loud so I can hear you.
What's your opinion of the IC engine and the range extender, and how do you put your thoughts about optimizing the designer on that hybrid, electric hybrid?
Are you thinking of the push me, pull you airplane that?
Just using an IC engine to get more range in an EV car.
Okay. His question, I think I understand it, is what do I think of putting an IC engine in like an eVTOL to generate electricity so you have sort of a hybrid? People are looking at that. There's all kinds of different ways you can get the energy needed. To be honest with you, all our work has been on the aerodynamics. We're doing nothing on battery development, nothing on ducted fan development. There's lots of people looking into these combinations. So I don't really know much about it, to be honest with you. Sir?
Professor Ullman, hello. I would like to comment that there is a practical airplane being flown every day where I live that's electric. And it's a sailplane that's towed up to altitude, and the electric motor is used to give them extended range to an airport for safe landing, which I think is an absolute perfect solution.
Right. And I didn't. His point is that there are electric sailplanes. You tow them up. They fly. If you need power, you can pop up the electric motor. It'll help you get to a new altitude, help you find lift. And there are some unique small places where electric airplanes do work and do make plenty of sense now. But that's such a small niche of what's being looked at, so I didn't cover that. But your point's very well taken. Sir in the red shirt.
So you're using these fans to shorten the takeoff, and once you get up to cruise, you just turn them off and they go to free wheel. How does that affect the drag of the plane normally? Is there any kind of plan to like retract these at some point, or what do you do with the fans after you take off?
his question was, you got these slats with these ducted fans in it on the wing, and what do you do with it after you take off? And he said, do you retract them? Do you just turn them off? What do you do? And the answer is yes. It turns out they're not as draggy as they appear, number one. Number two, we've obviously had discussions about retracting them and doing various things because it is a penalty. You can't help but be. And what we do about it in the long term, there are lots of options. One of the visions we have right now is that these things can be effectively mounted on an existing airplane. So take any airplane out here and stick these on the wing. And so you can't do the retraction there. But there's lots of games that can be played that we haven't even begun to explore.